complex solution. Notice that in the solution there is no I, right? You should not have an I in the final product. We use complex numbers as a, transitory phase in the solution, so to speak. Transitional. All right, here is another one. Calculate e to the ta, where a is 2502. Let's see here. So what did I do? Figured out a minus 2i is that, and then that squares to 0. So then that allowed me to just calculate it like that. So I'd say this one was a challenging problem. I think this might have been, this feels to me like there's something I did last year in lecture which led me to write this problem. I'm not sure I would have written that problem on your test if not for the fact that we just looked at this now. So, sorry about that. To whom much is given, Anyway, so to calculate the matrix exponential, there are really two competing ways we have to do it. We know if we have a solution matrix, we can calculate the inverse of the solution matrix evaluated at 0 times the solution matrix. That generates the matrix exponential. We talked about that, how you can use the solution matrix to calculate the matrix exponential. We derived that in class. So that's one way to calculate the matrix exponential. The other way to calculate the matrix exponential is just to brute force calculation. That really is only tenable if you can find the power of the matrix to an arbitrary order in some kind of nice way, like we could for I and j in that homework problem, right? Like I think we had j squared was I again. Was that one I gave you guys? We had j squared works out to minus I. Did I assign this problem? I don't know which course I'm talking about. Maybe that was from another course. I don't know. Anyway, there are sufficiently simple matrices that you can calculate their powers to arbitrary orders. And so you can calculate the matrix exponential by direct calculation. But this one here is basically the idea is that if I subtract off 2i, then powers of a minus 2i are really easy to think about. And then I can use the magic formula to create that a minus 2i series. And then since this truncates at order 2, I only have to calculate that much, and I've already got the whole matrix exponential is the idea. All right, anyway, let me not belabor that. There's many other more important things to talk about. Problem 4 is much like a problem you had on the previous quiz, right? Like the last problems. Y prime prime plus e to the xy prime plus sine 3xy. Find the first 3 non-trivial terms. And I gave initial conditions, right? So knowing what to do with these is very labor saving, right? This tells me that the constant term is 1. This tells me that the coefficient of x is 6 by the Taylor theorem. So really, if I want the first 3 terms, all I got to do is figure out what comes next. So I've got 1 plus 6x plus a squared, right? If you don't have that clear in your mind, the Taylor theorem, then this would be much harder. You'd have like a C0 and a C1, and you'd have to actually do some calculation. So if you're given initial conditions, make use of them. Okay, so then we just, the usual song and dance, right? Just plug it in and look at the constant term alone is enough to figure out a is minus 3. So this number 6, I think, is an awful lot like the problem I assigned you guys, isn't it? You have y prime prime plus 6x squared y, find the complete series solution. I mean, that is an awful lot like the one I actually gave you guys. And this one's also an awful lot like the one I gave them last year. So, but I'm not saying that if I gave you a series problem, it would necessarily be that one. I'm just saying that I don't, wouldn't be surprised if I gave one is my point, my larger point. Here's a Laplace transform problem. So, first of all, convert it to a sum of unit step functions, and then you take the Laplace transform of that, use the appropriate technology, you get this. It's important to know about, of course, trigonometry, expanding that as a sum of sines and cosines, because if you don't do that, you can't take the Laplace transform of that, right? So you got to know the trigonometry, otherwise you get stuck here, right? Inverse Laplace transform of that, so that's a partial fractions, that's s squared plus 9 times s squared minus 9, which means I'm going to have this partial fractions decomposition. And you do the algebra, and whatever happens, happens. So there it is. There's a unit step function with initial conditions, solve the problem. You had a problem like that in your homework, right? I mean, quiz. It's just one of those. Yeah, I'm planning to post this soon. So remember we talked about this theorem that if you find a series solution to a differential equation, then it will converge at least until the next singularity in the differential equation. So like this one has a singularity when this coefficient 0, which is going to happen at 2 plus or minus I. So my singularities in the complex plane are 2 plus or minus I. If I center my solution at 4, as is implicit from this, then the radius of convergence is the distance from 4 to 2 plus I, which you're going over 2 and up 1, right? So that's the square root of 5 in the complex plane distance by the Pythagorean theorem. So 4 plus or minus root 5 is the open interval of convergence. Now, I don't know what happens at the endpoints. That's anybody's guess about those, of course, but the open interval of convergence we can calculate just from this nearest singularity theorem. I often test on this, and I'm often depressed when I grade it. Anyway, then here's your token energy problem, and I give E1, E2, E3, 4, E5, E6, and ask to analyze possible motions. And I say if no motion is possible, explain why. Of course, there is one where no motion is possible, E1, because the total energy is less than the potential energy, which means that you can't have any classically allowed motion, because it would correspond to negative kinetic energy, which is, well, not good. And there's the XV plot. There it is. Oh, and that's it. So I think that's a good representation of what your test is likely to look at, give or take a problem. Yep. That'd be wise. Hey. I know, right? I said this to abstract algebra yesterday because we've got these problems where we're using colors to illustrate these different things called cosets, and like got 8 different ones of them. So if you had like 8 different colors, it'd be convenient. Because otherwise you got to come up with 8 different symbols to distinguish. It's kind of a pain. But yeah, if you had about some colors, it'd be good. I'll try to bring some if you want to borrow mine. Yeah, you can hit it.